And I'm very happy to introduce Katarzyna Rejzner, who's joining us from York University. She's actually a Brexit victim. She would be here, would have been for Brexit. But about the BV formalism and perturbative algebraic quantum field theory, and we look forward to that.
Thank you very much for the invitation, and I really regret that I cannot be with you in person, but my country that should rename nameless unfortunately made a total mess of traveling rules. But okay, well, we should carry on. Okay, so regardless, I'm giving this lecture on BV formalism, and there's a lot of explanation that has to be done. So let me start with some introduction. So the title of my lecture series is BV formalism in perturbative algebraic quantum field theory. So I will start by explaining the second part of the title, so perturbative algebraic quantum field theory. So let's get started with that. So first of all, pAQFT, so this stands for algebraic quantum field theory. And well, first of all, field theory. So we are going to talk about fields. We are going to talk about the situation where we're quantizing a system with infinitely many degrees of freedom. So this obviously brings some complications into the game. And quantum field theory is notorious for being difficult to describe mathematically in a rigorous way. So pAQFT, algebraic quantum field theory, is an axiomatic approach, axiomatic framework to try to make sense of quantum field theory in a mathematically precise way. So this is an axiomatic approach to quantum field theory. So let me start with a bit of a historical note. So everything starts on Minkowski spacetime. So just to recall you, so this is just R4 with a metric, which is Lorentzian. And I take the convention where we have 1 in the time direction and -1s in the space directions. So this is Minkowski. Okay, and the idea here is that we consider bounded regions O of Minkowski spacetime, and we want to assign to them the algebras of observables that can be measured, that can be considered performed in these regions. So to this, I want to assign A of O, which is the algebra of observables that can be measured in O. And in this framework, we typically assume that A of O is C star algebra. And sometimes more specifically von Neumann algebra. And this assignment of algebras to regions has to satisfy certain axioms. So it's an axiomatic framework. So axioms follow. So the first one has something to do with the notion of subsystems. So if we have O in O prime, so one region inside the larger one, then we want the algebras of observables to also satisfy this. So the algebra of the smaller region is contained in the algebra of the larger region. And this is called isotony. So that's the name for the axiom. And the next one has something to do with causality. So causality is one of the important features of quantum field theory. So quantum field theory is designed to kind of combine quantum mechanics with principles of special relativity. We know that special relativity tells us that nothing travels faster than light. So there has to be some remnant of the causal structure also in the QFT framework. So here it is. So in Minkowski spacetime, we can talk about various regions being space-like separated, time-like separated, and so on. So this is what the causal structure tells us. So if we have now two regions O1 and O2, which are space-like separated, I use this very suggestive notation of a sort of a light cone in between. So they are space-like. Okay, then I want the measurements performed in these regions to be independent. I want the observables to be independent. So I want A of O1 to commute with A of O2. So this axiom is called causality. Okay, so this is something very Lorentzian, very quantum field theory. And finally, there is some remnant of classical dynamics, so of actually well-posedness of the Cauchy problem, which is expressed as follows. So if we have a region O and we have a Cauchy surface sigma, so this is Cauchy surface. And for those of you who might not be so up to date with geometry, being a Cauchy surface means that every inextendable causal curve intersects it only once, exactly once. So every inextendable causal curve intersects it exactly once. So if we have such a Cauchy surface and then we take a neighborhood of a Cauchy surface, so let's call it N. Now, classically, if you look into PD theory, if you have hyperbolic differential equations on a sufficiently nice spacetime, if you have, for example, this Minkowski spacetime we are talking about, you have a Cauchy surface, then you can prescribe on it Cauchy data, which means essentially positions and velocities. And then if you have a sufficiently nice system of differential equations, then you can reconstruct the whole solution from the Cauchy data. Now, in the quantum world, there is something similar. Hence, you want to be able to reconstruct the algebra of this whole region O just by knowing the Cauchy data in this neighborhood N. So just by knowing the observables in N. So if we have such a situation, then A of N would be inside A of O in general, but here we want more. It's actually isomorphic to A of O. And this is called the time slice axiom. Okay, and I'm going to come back to these two axioms throughout the lecture. So these are, for me, the important axioms that are going to appear in various contexts when we generalize things going forward. So there are more axioms of AQFT, but they won't be relevant for this discussion, so I'm going to skip it. So for those of you who want to learn more, there is a book of Rudolf Haag, Local Quantum Physics, which is a sort of manifesto of algebraic quantum field theory. Okay, so this is how things were in the 60s. Now, we want to generalize this story. So the first generalization comes when we realize, okay, well, there are other spacetimes than Minkowski spacetime. There are black holes. There is, the early universe described by things like Friedman-Robertson-Walker spacetime. So we want to be able to do this story more generally. If there are questions, then please do interrupt me, because I know that this material might not be familiar to everyone on the same level. So the first generalization I want to talk about is locally covariant QFT. So this is generalization to a larger class of spacetimes, namely globally hyperbolic spacetimes. Okay, so what does it mean to be globally hyperbolic? So in simple words, it means that spacetime is globally hyperbolic if it has a Cauchy surface, actually. So namely, has a Cauchy surface. And actually, moreover, can be topologically can be written as that Cauchy surface cross R. So these are globally hyperbolic spacetimes. There is more information that I can actually say about it. So I prepared a little summary of, essentially literature on the geometry side of things. So if you want to find out more, then on globally hyperbolic spacetimes, there is the standard reference by Bernal and Sanchez, where they prove some very important theorems about the geometry of globally hyperbolic spacetimes. So initially, the idea of globally hyperbolic was actually described in a different way. So in physics, you introduced these spacetimes as spacetimes with no closed time-like curves, causal curves. So in a sort of more down-to-earth terms, it means that time travel is not possible in those spacetimes. So if you're a Doctor Who fan, as I've seen that Stefan is, this is not going to work in globally hyperbolic spacetimes, I'm afraid. I'm also disappointed. But here it is, here's what we can do. And then it was shown that such spacetimes satisfying this condition can actually be described as having a Cauchy surface, or equivalently having a foliation into Cauchy surfaces. So they're very good for causal structure. They have very good behavior of evolution of initial values in sort of classical terms. And for quantum theory, they are the spacetimes where all the constructions I'm going to talk about work. Sorry. Alrighty, so let's go back to the main plot. There is the next generalization that I'm going to talk about, and unfortunately, I have to disappoint Stefan here, because he just said that formal power series is not good enough for physics. Well, that's true to some extent. However, there is a big branch of physics that's still kind of dealing with the fact that they only have formal power series to play with, which is perturbative quantum field theory. So one of the problems with this nice axiomatic framework I introduced here with assigning C-star algebras to regions or C-star algebras to globally hyperbolic spacetimes is that it has a very small number of models in 4 dimensions. So unfortunately, in 4 dimensions, the only thing we can construct this way is free theory, and free theory, well, it doesn't tell us that much. And the interesting examples like the standard model of particle physics, quantum electrodynamics, and so on, these things cannot be yet constructed non-perturbatively. So the only thing we know is description of these things in terms of formal power series. So big disappointment, but yeah, we have to deal with that fact. So that whole nice framework here needs one more generalization. So we need to be able to describe perturbation theory. We don't talk about convergence. So this is where we have to get our hands dirty. Sorry, can you hear me well? Because my internet is telling me that there is a problem. Hello?
I couldn't hear one sentence, but then it was okay.
Okay, good.
You froze for a second, but we can hear you well.
Okay, thank you. I'm sorry. That's the problem of not being in the lecture hall, actually. Okay, yeah, so we have to be able to describe perturbation theory. And this is where perturbative pAQFT comes into the game. So P states for perturbative. Okay, and this allows us to treat a situation where A of O is actually a formal power series in H bar with values in, and now, well, C-star algebras is not going to work, but instead we want topological. Oh, sorry. There we go. Topological, unital, still want a unit. Involutive, so star algebras. Okay, so we have the involution. And this is the context I'm going to work with. Yeah, so that could be enough. But it turns out that from the point of view of the construction, it's actually useful to mix in one more ingredient into this, namely homological methods. So here at the beginning, I mentioned the BV formalism, and this actually is a toolbox which includes homological algebra as one of the tools for constructing models. So here homological methods enter. Hence, I want yet another generalization of this whole story. I want to be able to work with chain complexes, and more specifically, I want to work with differential graded algebras. So this is DG AQFT. So this stays for differential graded. Okay, and here A of O is, apart from being what's written above, it's also a differential graded algebra. Okay, so that's the sort of outline of what I want to do. So in the end, I want to be able to show you how to construct models of quantum field theories, physically interesting quantum field theories, by assigning differential graded algebras with some extra structure to regions of spacetime. Okay, any questions at this point?
Are you going to define the free theory?
Yes, I will.
Okay, great.
Maybe not today. Maybe tomorrow. Let's see how things go. I will start with classical theory. So that's probably today and tomorrow. And then I will define the free theory, and then I will introduce the interaction.
Great, thanks.
Any more questions? Okay, lovely. So I will start slowly because not everybody is up to speed with homology. So let me start with very basic definitions, and if people know it already, they can go and have a coffee. So let me start with a chain complex, which is going to appear a lot. So let me just define it properly. And we can do it over any commutative ring. So let R be a commutative ring. And if you feel uncomfortable with rings, well, in this context, we're always going to do it over C or from a power series in C. So these are the only examples. So a chain complex. So C with a differential D is a sequence of, well, in general, modules as follows. So we have some grading, so things will be labeled by integers. There's C0s, C1, C2, and so on. And we can also go in the opposite direction. So there's no reason to end things anywhere. And they're going to be these differentials here. And the important feature here is that D squared equals 0. So composition of any two consecutive D's is 0. And so this is a chain complex. Now we can revert the arrows and we get the cochain complex. So the cochain complex is something dual. So the arrows go the opposite direction. Okay, and now differential graded algebra is going to be, in particular, a chain complex. So, oops. So differential, stated as a definition. So a differential graded algebra over R is, well, first of all, a chain complex. Chain complex A of R modules. And okay, we want some algebra structure. So endowed with our bilinear maps. Sorry, that's my clock. It's telling me that I'm half time. So far, so good. So from, we have to respect the grading in some way. So we have AN and AM going to AN plus M. So AB goes to A times B, such that, and well, there's the obvious Leibniz rule, which shows the compatibility of the differential with the product. So dn plus m on AB is dn of A times B plus, and there are some signs. There's going to be a lot of signs, unfortunately, throughout this story, D, M, B. I will try to keep my signs consistent, but I cannot promise anything. Okay, and this whole collection of ANs is associative and unital. Okay, so that's what I want from my structure. And well, similarly, I can also have a dual version. So also a cochain complex. So the differential graded algebra is either a chain complex or a cochain complex, or cochain complex, where again everything looks the same, but the arrows are pointing in the different direction. Okay, so that's a crash course in differential graded algebras. So two things to remember from this. So chain complexes, we have a differential that squares to 0. We have grading. Differential graded algebras, we have that same thing. Plus, we have compatibility with between the differential and the product. So we have a graded Leibniz rule. A very important thing later on. So now, having this structure, we can define homology or cohomology of our chain complex. So here is some nomenclature that I'm going to use. So first of all, the elements of the kernel of D, they are called, well, depends where we are, but in chain complexes, they are called cycles, cochain complexes, co-cycles. So this is co-cycles. Elements of the image of D are called co or no co boundaries. So in other words, so cycles are closed, boundaries are exact. And now the homology Hn is defined as the kernel of D at degree n quotiented by the image of D at degree n plus 1. And the cohomology, very similar. So kernel Dn over image Dn minus 1, because the arrows are pointing the opposite way. So we are going to be looking at these homology or cohomology groups in concrete examples that we want to look at. And the basic example of a differential graded algebra that everybody knows is the DRAM cohomology. The RAM cohomology. So here you have the differential forms on M. So M is some smooth manifold. So n forms. So you have the de Rham differential D, right, which acts on forms, and you have the wedge product to put forms together. So you can, well, I'm sorry, I'm not running exercise classes because I thought it makes a bit less sense online, but you can do the exercise yourself at home and check that this is really an example of a structure we are talking about. Okay, and then you can also, as an exercise, try to compute H0 for the de Rham cohomology and see what you get. Cool. So that's the crash course in homology and cohomology. I'm not going to go too deep into it, but it's good to know the dictionary. Okay, another tool that I'm going to use is a tiny bit of category theory language. So I like to talk about things being factorial because it's a very nice way of saying natural and compatible and generally speaking, very, very nice. So I'm going to use that language. If you are not very familiar with that, don't worry. It's also understandable without category theory, but I think it's nicer if you state it this way. So I'm going to now introduce a couple of categories, but they're not very scary. So first of all, I'm going to start with fixing a spacetime M. So this is a spacetime on which I'm going to construct my theory. So I assume it to be globally hyperbolic. I also give it time orientation. And in this spacetime, I consider a certain family of open subsets. So I define cos M as the collection of relatively compact, connected, contractible, so generally speaking, nice, causally convex, well, open, I said open, but I should write it down as well. Open subsets O in M. Let me also explain what I mean by causally convex here. So it means that it contains all its causal curves. Contains all causal curves. With endpoints in it. I think it's useful to draw a picture at this point. So my O is causally convex. So if I have, so if I have a causal curve that starts, let's say, finishes here and starts here, it has to remain inside this set. So it could do something like that, but it cannot do something like that. So that wouldn't be allowed. So that wouldn't be consistent with being causally convex. Okay, so this is my, there is a question. Oh, yes, okay. Let me do an excursion into geometry. So that's let's start with Minkowski spacetime. So let me draw. So the question was, what's a causal curve? So let me just explain a bit more about the geometry of the problem. So in Minkowski spacetime, we have space and we have time, and we have our lovely metric, which is just a diagonal metric with minus here. The wrong convention, with 1 at the top and minus ones here and zeros elsewhere. So now we can look at classification of vectors in this situation. So let's take a vector v in R2. So if g of v, okay, so this is now very simple. So v transpose g times v, this is just algebra. If g applied to v is 0, then we say that this direction described by this vector is light-like. So v is light-like or null. So such directions would sit here on the diagonal. So we're in 2 dimensions and form something called the light cone. Okay, so this is being null. Another possibility, this could be strictly less than 0. Actually, let's start with strictly larger than 0. So then this vector v would be inside the light cone. And this is the situation where v is time-like. And it can be pointing into the future, or it could be pointing into the past. So this is time-like. And finally, there is the situation where g of v is strictly less than 0. And this is the situation of v being space-like. So then it's pointing here, here, so anywhere outside the light cone. So that essentially describes the situation I talked about before. So things being space-like are kind of sort of independent, because according to Einstein, information cannot travel faster than light. So all the observers, everything has to kind of evolve, propagate inside the light cone, and there is a preferred direction of things. So information observers go from past to the future, staying within the light cone. Now, what's causal? So a vector is called causal if it's either light-like or time-like. So this is a causal vector. Now, with curves, it's actually very simple. So a curve is called causal, light-like, time-like, space-like, if the tangent vector is of that form. So I have curve gamma, and I have the tangent vector gamma dot. So gamma is causal, space-like, or so on, if gamma dot, the tangent vector, is causal, space-like, and so on. Okay, so that was the excursion into geometry. Is it clear now what I mean by those things?
So is it allowed that gamma can just stop and then go back in time?
In what sense?
In the sense that, let's say for t negative, let's say for t positive, it will do exactly the same thing as for t negative, but then in the other direction, where t is.
Well, right. So there's so first of all, we want to have smooth curves, so we cannot do something too crazy. Well, I mean, yeah. So I have to be able to draw it, and unfortunately, I cannot really visualize it. So you mean the situation where we are going up here, then stop, and go down here?
Exactly.
Well, but that parameterization, yeah, I'm not sure if that would actually, well, no, that wouldn't be differentiable at that point, would it?
Well, if you just.
Oh, if you're just stopping.
I think so. Anyway, it's not that.
Yeah,
important.
no, that's probably fine.
Okay.
Yeah. So, but yeah, when typically once so for all the definitions, you want things to be future directed or past directed. Yeah. So there is this additional time orientation to take into account.
Isn't the convention where you make the origin just space-like?
Sorry?
Where you make the origin space-like, where you require that the origin, I mean, this is just a word, that you include the origin 0 in the set of space-like vectors.
Well, yeah, I mean, it can belong, yeah.
So it's
well,
just
the 0, yeah, the 0 vector, you could argue. I mean, the 0 vector, I think it's fair to say it's included in the light-like, but yeah, I mean, just for consistency, right? So for consistency, I would include 0 vector as causal, because I mean it is on the light cone. It's on the apex of the light cone.
I know a different convention, but that's okay, of course.
Oh, I think, well, yeah, okay. It doesn't matter that much, but yeah, I guess you could also do the other thing.
The 0 vector is causal. Don't you then trivially have closed causal curves?
Sorry, if what?
If the 0 vector is causal, don't you then trivially have closed causal curves? By the argument Luke just gave.
Well, I mean, do you have, I guess the question is that would probably not be inextendable though. Okay, I would have to look it up, sorry. I didn't prepare that for the sake of this lecture. I can check the exact definition in the reference, because that obviously wouldn't be allowed. So there must, yeah, I apologize.
No, sorry for the annoying question.
No, it's fine. It's fine. It's fine. It's just me being incompetent, but I can check it for the next time. I'm not a real geometer. I just pretend to know some geometry, but obviously that's a very good question. Can I go back to the main course of the lecture, maybe?
Please.
Thank you. Okay. Okay, so yeah, barring the exact definition of what does it mean to be causal in this context, So this. Okay, so yeah, so that collection of relatively compact, connected, blah 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 open sets is going to form the set of objects of the category I want to consider, and the set of morphisms are actually given by inclusions of these as subsets of M. So these are the objects, and morphisms, these are inclusions. Okay, and this together forms a category. And so that's one category. And for the classical theory, I will look at the target category for my classical theory functor, which will look as follows. So I'm going to denote it P alg star, the category of differential graded Poisson algebras. So this is something that Stefan already introduced. And for future convenience, I also want involution. So these are involutive Poisson algebras, and I'm interested in constructing a functor into that category. Okay, and because I'm also going to, try to formulate this in a bit more abstract way, let me now define what I'm going to mean by a differential graded classical field theory model. So a DG classical field theory model on a spacetime M is a functor P going from cos M to P alg star with the following properties. So here I want to preserve the two axioms that I gave before. So there is the causality and the time slice axiom. So I want to bring those over, but in a slightly weaker sense. So causality has to hold on homology level. And time slice axiom also holds on homology level.
Sorry, could I ask
Yes.
two short questions?
Yes.
The first one is, what are the morphisms of your Poisson algebra? Are there just Poisson algebra morphisms?
Yes, of course, yes.
More general, like reductions? Or?
No, just the, well, yeah, I mean, these are well, there's certain levels of that, but there are the chain complex Poisson algebra star morphisms.
The other thing is the inclusions are just strict inclusions, no inclusion up to isomorphisms or diffeomorphisms.
Here in cos.
Yes.
Yes. Just inclusions. Yes.
Is there a compatibility between the involution and the Poisson structure?
Yes, there is. Well, I mean, yeah. Yeah, the involution has to be compatible with the Poisson structure.
Okay, thanks.
Yes. Okay, any more questions? Okay, well, so there's this slightly weaker, slightly weaker requirement that these axioms hold on homology level. So you can imagine that taking homology of that DG classical field theory model would give us a strict, honest to goodness classical field theory model. But it turns out that it's more useful to actually look at this derived version of things and look into this homological construction because this is much more convenient for quantization, especially of things like gauge theories, where actually that whole homological power comes into action. Okay, so the rest is about explicit construction. So I think it's maybe a good time to pause because, yeah, I think that's probably enough on the side of introduction. And tomorrow I can start working through the explicit construction of a functor satisfying these properties. Maybe I should also give the definition for the quantum functor. So eventually, sorry, somebody's calling me nonstop. So yeah, in a similar way, I can also define a DG quantum field theory. So this is going to be the same, but from a category of involutive algebras, now not Poisson anymore, but with formal power series in H bar. Sorry. So this is a functor A from cos to oops. Yeah, I think my computer is telling me very precisely that I should stop talking now. That's yeah, that's it. Well, okay. I will come back to this point tomorrow, but yeah. So the quantum field theory functor, I can say it in words, is again a similar structure. So causality, time size axiom hold on homology level, and the category is the category of differential graded involutive algebras. Well, yeah. No, formal power series in H bar with coefficients in those differential graded involutive algebras. Okay, so that's going to be the setup. And yeah, sorry for the technical issue at the very end. Thank you very much.
Thank you very much, Kasia, for your brilliant talk.
Are there any questions? Any more questions, meaning?
I have a question. So what is a differential graded star algebra? This is, I guess, not as harmless as it might seem, because you need some kind of compatibility of the involution with the differential, right? Or do you completely ignore the compatibility?
sorry, just a sec. Yeah, that's going to go on for a bit. No, it's not completely harmless. Yeah. Okay. Well, you can look into our paper with Owen William for the precise definition of what we mean by that. I mean, we are very silly with this. So in the concrete construction, this involution is just a complex conjugation of functionals. So that's pretty harmless. But I mean, more abstractly, I realized that this is a bit more subtle.
So it commutes with a differential.
Yes.
Okay. So then you will have issues with positivity, right?
Yes. We completely ignore those issues. Yes.
That's what I wanted to ask. Yeah.
Yes. No, I mean, yeah, it's yeah, on that level, it's maybe not so relevant. But in general, yeah, one would have to worry about these things a bit. Yes.
Sorry, I had just another short question. Will you be thinking about states, Hilbert spaces?
Oh, no.
Okay, thanks.
No, I mean, not that I don't want to, but it's just 5 lectures, so there is a limited time. But it's a bit awkward because what one considers here is only well, representations of what you get on the level of homology. I can comment maybe on it when I get to the actual explicit construction, how people go about constructing states. I will talk about states in free theory a bit, but yeah, this is, again, I can tell it in a concrete example. I don't have a clear picture how it works in the general setup, because Hilbert spaces don't like formal power series and homology. Oh, and there is a question, is there a sheaf interpretation of some kind? Yes, there can be. So I'm not going to require any sheaf property, but there is a very nice formulation of these things using factorization algebras, where you have some sort of sheaf condition on a slightly more exotic topology. But yeah, so one could require some gluing properties. Sorry, I had to turn off my camera because my computer is really not cooperating. No, we do not assume a C-star algebra structure. That would be great, but no.
Could you elaborate on the factorization algebra thing? Is there a statement of the form, maybe if you Wick rotate this setting, you get a factorization algebra or something like that?
Okay, I think I managed to get my camera to work. Yeah, well, you don't even have to Wick rotate, in fact. So the paper I mentioned with Owen William, we showed that you have a factorization algebra already on the Lorentzian side of things. Yeah, I mean, for the free theory is quite obvious, in fact. I probably can also say a few words about it when I get to the concrete construction. So you have to encode your causal structures somehow. So in factorization algebras, sometimes you have this property of being locally constant. So that you have an open inside a larger open, and then you have a quasi-iso. Now here, this property would have a sort of time direction. So things will be locally constant in time direction. which corresponds to this time slice property. So there is a parallel story I could tell about like all this construction in the language of factorization algebras, which would also make sense in that setting. Interesting.
And what does causality correspond to?
Well, that corresponds to exactly this preferred direction, that your structure is locally constant if you look at these, larger and larger time slices.
But that's the time slice axiom, right? Or
yeah, but somehow you have both, because you have the factorization product on the sort of time slice. So you have commutativity of disjoint things in the space-like direction. So that just comes from the factorization product. And then the sort of, So the difference between the time direction and the space direction then comes from this local constancy. So in a sense, this covers both bases, both axioms, plus obvious, properties of the factorization product.
Fascinating.
Okay, so thank you everyone for your questions and for your attention, and in particular, thank you, Kasia, for your nice talk.
Thank you all. See you tomorrow.
And we'll take a short lunch break now until 1:30, and then we will reconvene for the next lecture.